Hi, Prof. Of course. I think we can. I just
We
started the
still-
lab.
Yeah, we have
Yes,
4 minutes more.
of course.
But I'm there.
Perfect. Thank
Yeah.
you so much, Prof. Hi, Prof.
Welcome. Hey. So he was saying that
Hey, Priya, good evening. Can anyone hear me?
Yes, Daniel.
Daniel. Yeah, good evening, Daniel.
Okay, cool. Good evening, everybody. Okay, thank you for joining us for the evening section for this week on our Breaks Data Analytics program. I'm glad we all made it. I'm happy many of you have continued to join the section. And as we progress for the remaining part of the workshop, we had our first section in the morning. This is week 5. And then Priya and Alexi take us through astronomy data sources. Yeah, and how to handle FITS file. We'll continue the evening section the same way. Please do mute your mic.
check-in has been done.
Yeah, can you hear me? I'm not sure she can hear me. Okay, yeah, so please kindly mute your mic until it's time for the presenter to open up the floor for questions. Yeah, and this meeting is being recorded and it's also being streamed on YouTube in case if you miss out a part of it and want to watch it later. So it's exactly 6 p.m. Over to you, Priya, and take over from here.
Yeah. Thank you so much. Thanks, Lebo. 1 minute. Yeah, thank you very much, and welcome everybody to this session on data analytics. So Today's session is actually dedicated to astronomy data sources, and that is why it's a very important session, because basically when you are plan your capstone project, etc., you need to know where is the data sitting, where can you get the data from, and that's what we are basically going to talk about. What are the data sources from where you can get astronomy data, and then one can actually plan on what you want to do with that data. Okay, so I hope you can see my presentation. Yeah, is everything fine?
Yeah, it's fine. We can see it.
Yeah, great. Okay, and it's on YouTube too, right? Oh, that's fine. Okay. So, like I told you, today what I'm going to be talking to you is about data-driven astronomy. Basically, that is basically about the data which is available in astronomy, and a lot of this data is data from uh, ground-based telescopes as well as space-based telescopes, and especially the space-based telescopes as well as the ground one. A lot of them have a very good data sources. The idea basically being that we want the data, astronomy data, which is basically done with very big telescopes which cost billions of dollars. One would like to get out the maximum science from those sources that we can, right? And that is why I'll just show you this. Yeah, so that's my email. You can always write to me if you have questions, and I'd be happy to answer. Yeah. So what happens is, what is the kind of astronomical data that we have? So some of them, what happens in astronomy when you have big telescopes, you can work in two modes. One mode is what is called the survey mode. That means the telescope basically observes the whole sky. Okay. And for example, if it is Gaia is an ESA telescope which basically looks at stars essentially in our galaxy. So what happens is, as it keeps scanning the sky in the whole lifetime of Gaia, it'll go to the same star at least about 70 different times, right? 70 times. So what happens is, it'll give you measurements 70 different times about the same star, right? And like I said, because it's an all sky survey, it's not a pointed observation. It is all sky. Therefore, what happens in this case is, is because it's a space telescope. It's very specialized data, and therefore, what happens is, like for Gaia, you have something called a DPAC, which is the Data Processing and Analysis Consortium. So what they do is, the data that comes from Gaia, it first goes to the DPAC, and then the DPAC does the basic processing in the beginning. And then once it's in a position to be used by anybody else, they then have what is called a data release. Okay. So they have had different data releases. For example, with Gaia, there's been a data release 1, 2, then there was an early data release 3, and the last data release is data release 3. So there's EDR3 and there's DR3. So in short, if you want to study any part of the sky, you can actually use Gaia and it will be available. Similarly, this works, for example, in infrared. There's something called TUMAS, which is an all sky survey in near infrared. And then if you wanted longer wavelengths, there is what is called WISE, and WISE will give you in mid infrared, etc. So you can get data from that. So these are survey based telescopes, okay, where you can get data for any part of the sky. Now, telescopes could also be on what is called observatory mode. Okay, for example, James Webb. James Webb is a 6.4 meter telescope out in space, $11 billion, right? And basically, what happens is, as the size of the telescope increases, the field of view becomes smaller, right? And therefore, what happens with the James Webb, you cannot scan the whole sky. That would be impossible, right? And therefore, what happens with the telescope like James Webb, or for example with Hubble, is that if you want to observe with it, you actually send a proposal. You send a proposal that you want to observe so and so object with James Webb or with Hubble. Okay. And then what happens is, the telescope has what is called a time allocation committee. Okay. This is often what is done even on ground-based telescopes. So you have a time allocation committee which assesses the proposals which have been submitted to observe with that telescope. Okay. And then, purely based on the credit of your proposal, the science case, what are you saying? Why do you want to use the telescope? What the purpose? What are is the science case valid? is the method of analysis, etc., that you are proposing, is it is it worth it, is it meritorious? Based on that, the time allocation committee allots you time. Okay, now this is very democratic, because in this case what happens is, this is purely merit based. Okay, this is not based on which country do you belong to, or the other factors. There could be some reserved time for different countries if they have pooled in money for the telescope. But typically for time allocation committee, anybody from anywhere of the world can propose it, right? And the only factor which decides whether it gets accepted or no is its merit. Okay. So it all depends upon how good or bad your science case is. Is it worth it or not? And based on that, they decide whether they would like to give you data or not give you data. Okay, so this is a very good thing, because what happens is, based on this, you can actually see, you are getting it basically based on your merit. It has got nothing to do with your with whether you're paying money for it or something like that. So that's a very interesting thing, that in astronomy now, especially if you want to, like I said, even if you want to observe with James Webb, you can observe with James Webb, right? You do not need to have contributed money or belong to a certain country. You can still observe with James Webb if your proposal that you give, if that is considered worth enough. Okay, then you can very well observe with James Webb. Similarly, all the archival data which I will be talking about today, all that also can be used by anybody anywhere in the world. So if we can go back to observatory mode. In observatory mode, you, for example, have given a proposal to observe a certain object. Okay, so for a certain period, it varies for different telescopes. It could be 6 months, it could be 18 months. For a certain period, because you are the one who gave the proposal, your data is considered, it's called proprietary data. Okay, that means it's a data which belongs to you. Nobody else has given that data, because you are the one who gave the proposal and actually managed to get time on the telescope and get data. So that is your proprietary data, okay, for a certain period of time, which is, like I told you, it could be 6 months, 18 months, whatever it is. But once that period is over, once the proprietary data period is over, then again all observatories, space-based as well as ground-based, they then make all this data public. Okay, so like I told you, if it's survey data from the beginning itself, you get it. And even if it is through a time allocation committee, after your proprietary data period is over, the data is available to everyone. Okay, now this is this could be very high quality data. For example, James Webb data, that's the best data you could ever dream of, 6.4 meter out in space. You could be using VLT data, which are 10-meter telescopes. So all these different telescopes, etc., their data is available. Okay, you have to basically just go to their websites and look for the data that is there, right? If it is proprietary data, then you can actually check about what did the person who asked for the data, what did they actually do with the data, right? Obviously, it doesn't make sense you're repeating what those people have done. But if you can think of something to do with that data which is different, which is unique, different from what the proprietary guys asked for, then you can actually use it. Similarly, even normal archival data, supposing you're using Gaia data, all you have to do is just check. That's the problem with archival, that since it's available to everyone, you have to basically check what is the work that people have done with that data. Okay, what is the work they've done? And as long as you can prove that the work that you are doing is unique, right, it hasn't been done as yet, then in that case your data is valid and you can actually get out good results. And you can get out excellent publications, etc., which with this data, because like I'm saying, this is very high quality data, right? So for your capstone projects, you could use data of various sources: Hubble, James Webb, Kepler, TESS, Gaia. There are many different sources through which you can actually take data and actually plan a capstone project. So capstone project, one can even work on, if you find some data already on which there is a paper, A capstone project needn't be something that has never been done. So you could even follow a paper and try to work it out. And then you can, once you understand how to work it out, you can then work it out on another source, right? So you first work out a paper with a source which is there. And then once you confirm that you understood how to use it, you can then apply it for other sources. So in short, there are many data sources. There's also the ESO, European Southern Observatory, VISTA data. The other very big thing is the Vera Rubin telescope, which is looking at transient sources. And then there are also data of simulations, the TNG simulations. So what basically happens is we require to have what are called data centers. Okay. So yeah, so there's a question by Sai Vignesh. Can we work on atmospheric dynamics too for your capstone? Yeah, you can. It's fine. You can do that. So, in short, therefore, what happens is all this data, which is there from space-based or ground-based telescopes, they are kept in what are called data centers. Okay, so basically, data center is a set of computers and a strong hardware where the data is actually residing. Okay, now often what happens is for the same data set, there are more than one data centers. Okay, because based on your location you may actually choose a data center which is closer to you. It could also happen that some data centers could have some kind of maintenance work going on or something else. So it's always good to have more than one data center, and therefore we generally have more than one data center where you can actually
Because
look
based on
for
your location,
get your data, etc. So more than one data centers do exist. Okay, and that is used by people. Okay, so now the data centers in astronomy, I think Alexei will talk a little bit about you. The data in this is basically kept in MySQL format, okay? Because for big databases, that is the most efficient software. And therefore, in astronomy, we have something called ADQL, which is Astronomy Data Query Language, which is very similar to MySQL, which is used to query the data centers. Okay, you could also query the data using Python, and there are Jupyter notebooks. Often in many websites, you also have sample Jupyter notebooks, which actually show you how can you query the data and get the data which you are going to be using. Okay. Now, let's come on to what kind of data do you have? What are the different types of data sets which you can have? So, the fun kind of data you can have are images, right? This is like a picture. You could have an image of a source. It could be a star, it could be a galaxy, it could be whatever you are looking at. So, that is an image, okay? And we will see what are data cubes. So, what happens is the image can be taken in different wavelengths. In astronomy, we basically use filters to define wavelengths, and you may take your image in this thing. So, Fana is asking me, can I use Kaggle to obtain a data set for the project? Yes, you can. You can use it, but in Kaggle, most of the data sets, I don't know whether they are astronomy data sets. Most of the data sets are of different kinds. So, just look if it can be astronomy or at least something scientific, then that would be good. Because otherwise, the typical Kaggle data sets are, the ones on Titanic and on sepals and stuff like that. So you just check out what are the data sets. It's not so difficult downloading the data, so you don't need to worry so much about that. Okay, so those are what are called images. Another thing is the data can be in the form of what are called catalogs. What is catalogs? Catalogs are basically tabular data. You have data, say you have an image and you have a table which tells you the number of sources in that image. So it tells you their RA, their depth, their brightness, their various parameters, and that is in a tabular format. So those are what we call catalogs. Data can be also in the form of what is called a spectrum. What is a spectrum? Spectrum is the brightness versus wavelength. That means you're looking at an object and seeing the difference of its brightness at different wavelengths. Okay. The other kind of data set now we have is what is called time series. So now we know in astronomy that most sources are what we call transient sources. What are transient sources? Transient sources are sources which actually vary with time. The brightness varies with time. So typically when we are, for example, Okay, I can see another question. See, about the capstone project, I don't know. You ask the organizers. They will tell you about the deadlines for the capstone project. I don't know. But we have another question from Nathan, a little bit unrelated. Would humanity worry that constructing data centers would someday make the Earth run out of space, or would innovation make the storages smaller while carrying more data? So actually, we have miniaturized all our data sets. If you see the amount of data that gets stored in your phone, right, which is a small handheld device, this was the kind of size which were there on computers when we were students. The kind of size we used to have on computers, they used to be 256 MB, etc. While now your phone itself has memory in GBs. So actually, it's not that data centers take a lot of space. You are probably confusing with the data centers that is nowadays being used for machine learning and AI, right? Those are slightly different kind of data centers, which are, which are not very good for the environment, right? And it has various other issues about having those data centers. Those are the ones which are the ones handling ML and AI. But agreed, even these astronomy data centers, they do use a certain amount of machine learning and AI, because when they've got to sift through all this data, right? There's so much of data which is available, then obviously they do use some machine learning and AI techniques. So yes, those are issues, but we won't talk about that. So in short, what is time series data? For example, if you have a star and you have an exoplanet going around it, so the planet does not give out any light. So when the planet comes in front of the star, the brightness of the star falls. Okay, and that is called the light curve of the star. And therefore, so typically there are two space telescopes. One is Kepler and one is TESS. Both these telescopes give us light curves for stars, which can be used for the study of exoplanets. And that is a very good capstone project to do, because you can use Kepler test data to get all the parameters of an exoplanet. For example, get its exoplanet's mass, radius, temperature, orbital distance. You can even answer the question whether you think the exoplanet could be habitable, right? For habitability, the definition we put is that a planet is considered habitable if water is present there in a liquid form, right? So what happens is, therefore, you can, since you are for the exoplanet, you can calculate its mass and radius, right? Because you know the mass and radius, you can actually calculate the density of the exoplanet, which is mass upon volume, right? So you can figure out whether the exoplanet is a gas one or a rocky one, etc. You will also, through these calculations, you can find out even the temperature on the exoplanet. So you can answer the question whether water would be present in liquid form on this exoplanet, right? So in that way, time series data can be like that. Time series data can also be variability of any other sources. There are many variable stars, there are galaxies, active galactic nuclei, many such variable sources for which you have time series data. So time series also is tabular data. You will have brightness versus time. You could also have polarization data. Polarization data is very important to study the magnetic fields. So if you want to study the magnetic fields in sources, you may use polarization data. Okay. So let us talk about images first of all. So what are images? The kind of images we get in today's time are what we call digital images, right? A long time back, people observed with photographic plates. Those are what we call analog images, okay? Digital images are images. How do we get a digital image? A digital image is like a 2D array, okay, in which you have boxes. These boxes are called pixels. Pixels, or it is a picture element, okay? That's a pixel. Now, a pixel, obviously, the more pixels you have, the better resolution you will have of your image, right? So typically, when you have cameras, digital cameras and all that, you would like them to be 5 mega or 10 mega or whatever, so that you get good images, right? So the number of boxes you have, the number of pixels you have, will tell you how good is your camera. Okay. Now we use these images. I will explain to you how do we make RGB images as well as artificial images using these things. But just remember that a digital image is nothing but a 2D array where every point has a certain brightness or a certain value, okay, which tells you about the light falling on every point. Now, these images can be of two types. They could be point sources like stars, or they could be extended sources like galaxies. Okay. Now, what is a digital camera? A digital camera is what we call a CCD, or a charged coupled device. What is a charged coupled device? Now, a charged coupled device is actually this. Okay. So I will. Okay, no, I will continue with this. So a CCD is basically, like we saw, it's a grid, right? Now think of the grid. Supposing you had a grid of buckets, okay? You had buckets like this over here. Now you expose your bucket to light, right? Which is basically coming through photons. So in every bucket, you collect a certain amount of photons, and the number you collect in every bucket gives you the count, the photon count for each of the buckets, right? So you will get some number over there. Now, so these guys, Boyle and Smith, these guys in the 60s, they developed this thing, and then in 70s, they actually got a patent for it, for what are called this thing. And this is what is the heart of what is called a digital camera. So typically what happens is this works on what is called the photoelectric effect. What is the photoelectric effect? That if you have a surface on which photons fall, because photons fall, they give energy, and therefore electrons get released. And when electrons get released, you get a current. So what happens is on each pixel, you measure the current. Now, the more the photons fall, the more will be your current. So that will also tell you. Okay. Yeah, so I see there's another question from Sampreet Das. You talked about a few types of astronomical data types like time series or images. What type of data do redshift surveys generally store? So redshift surveys are basically spectroscopic data. I will explain that to you in a short while. Just give me 2 minutes. So here are my CCDs. So typically, what is there in my CCD? A CCD, I will just put this over here. A CCD, like I told you, is this grid. Okay, you have an array of buckets. Okay, now what we do in astronomy typically is that each point, right? Each point, we actually put a filter on it. Okay, what do you mean by a filter? A filter will only permit light of certain wavelength. Okay, so for example, if you put a green filter, it will typically permit light of 5,000 angstroms. If you put a red filter, it would allow something like 7,000 angstroms. If you put a blue filter, it will emit something like 3,000 angstroms. So you have all these different filters. So like you see over here, if I have a blue filter on my CCD, on the pixel, what happens is the picture element or the bucket we were talking about. So the photons fall on it, but only the blue photon will be able to pass through it because it has a blue filter. Similarly here, if the photons fall on it, only the green photon will pass through because you have a green filter. So it actually counts. So what is there on this typical CCD or a digital camera is that half the pixels are all green. Why? Because green is the in-between wavelength. It is 5,000 angstroms. It's in between. The longer wavelength then is red and the shorter wavelength is blue. So what happens is half the pixels are all green because that's the average wavelength. And then 1/4 of them are blue and 1/4 of them are red. So you let light fall onto this object, and then at each point, you will actually get some count, right? You'll get some count over here, etc., etc. And when you add it up together, you will get what is called a RGB, or a red, green, blue image, right? Now in astronomy, this is what happens in digital cameras. In astronomy, we do something else. What we do in astronomy is that when we expose the CCD, we put the same filter on the whole CCD. Okay. So for example, you have a red filter, you have a green filter, you have a blue filter. Okay. And then what you do is each time you expose it to a filter, and then you get some counts from the red filter, you get some counts from the green, some counts from the blue filter, right? You get different set of counts. Now what happens is you combine all this together to get what is called the RGB image. So I may use the count of red, green and blue, add it all together and use that to get my RGB image. So this is how we get RGB images in astronomy. This is how you do RGB images, say in a digital camera. In a digital camera, you have this. I can see that there's some other questions. I will just try to answer them. Sampreet Das says, ma'am, you talked about a few kind of astronomy data types like times. Okay, okay. Should we choose? Okay. Don't worry about the capstone project just now. Please listen to the lecture, okay? And then later on, you worried about the capstone project, okay? Later on, you worry about the other things. Okay, so this is how we work in digital cameras. This is how we work in astronomy data. Okay, so typically in astronomy data, what we do is if you're looking at an object, you do filters in succession. Okay, so we use different kinds of filters: blue filter, red filter, right? They are often given even by alphabetical. In infrared, near infrared, we have JHK filters. So you can have different kinds of filters, and you take images in different filters. You take it in succession, and then you overlay those images. You take them all together and place them one on another, and then you add it up for actually getting the actual image. So you can see this is an image of a cluster called Vestalin 2, and this is with a 2-meter telescope. And the right telescope here, you can see this one is with Hubble. So here there are different sets of filters and different ways in which they are. So now, because images in astronomy are of a different kind, like I told you, which are called, what do you say, digital images, there is a separate format in which these images are stored. So, typically images are JPEG format, PNG format, GIF format, TIFF format, right? But in astronomy, we have our own format, and that format is called FITS, Flexible Image Transport System. So FITS is the format in which we actually have images. So what is a FITS image? It is made up of different parts. One part is the counts, which I showed you, right? A 2D array which has counts. So that is the basic image, okay? The 2D array with counts. The other important component in an image is what is called the header file, or the file which has what is called the metadata. Okay, so the header file is different kinds of things. For example, if there's an image, it will tell you which telescope was used to make the image, right? What was the exposure time? What was the filter used? What was the coordinates of the object you observed, right? So all these kind of things are what are called metadata. So these are also called headers. So with every image, you stick it along with a header, because the header will have this mega data about the image, so that otherwise if you keep them in isolation, you'll always have confusion as to which image was taken from where. And therefore it's all packaged together. So in the FITS format, you have it all sitting together. The header file, which has the metadata for that image, and the FITS, which is the image file, which have that stuff, right? So all these other things are also fit along and added with these images. You also have an image, so you can see this. This is again what I was talking to you about, digital images. For example, this is a digital image. Only the parts where H is there, the lettering, it is 0, and the outer parts are 1. You could have an image with the reverse, where, for example, all the parts which have H, so this is black and white. That's why the H part is 0 and the background is white. You can have the reverse of the image also, where, for example, the H part is all white, is all white and 1, and the other part is 0 and black, right? So you just have a count which is placed along this. Similarly, if this is an image, this is an image, this is the image, you basically have a set of counts for every point, and based on that, you're basically making your image. So your image can be 0 to 255, right? Which will make up your image, depends on this thing. If you have a 16-bit image, right, then the range for each pixel can range from 0 to 65536. 65536 is 2 to the power of 16, because each you'll have 1 bit per for every this thing, so it becomes 2 to the power of 16. So the different range. So if all these 3 images are of the same object, okay, this is of a cluster called Vestalin 2. It's the same image, but if you look at this image, you can hardly see anything, right? Alexei will show it to you using DS9, but if you understand the concept of it, you see that the count on all these points is any number between 0 and 65,536. Okay. Now, obviously, because you have such a large variation, it's very difficult for you to see any object. Okay. But now the second image, which you can see, we know that the range of the numbers which we have at different pixels is something between 4,500 to 7,000. Okay. So if in the middle picture you can see, I know that my scaling is from 4572 to 6,000. So I actually put cutoffs, right? So I only count the pixels starting from 4,000 to 7,000. So these numbers 6542 and 6002 will come within that, right? So then if I cut it off like that, then this is called linear scaling. Then for each point, I'll get a count, and that count will give me the image. So you will see it in DS9. Alexei will show it to you, how you can actually get this different contrast, right? So that you can see an image. The third image you see is what is called square scaling. This is called linear scaling. This is called square scaling. In square, what happens is each point, the value you get on it, you square the value, right? So in this way, you kind of increase the contrast, okay? Because you've squared all the values over here. So the third image is even an improvement of the second, which is an improvement of the first. So what we do is in astronomy, for images which we get, we do a lot of image processing. We do various things with the images so that we can see more from the image than is directly visible. Okay. So we do various things to accentuate features in the image so that you can actually see it, right? So you do these kind of things. Okay. So, Alexei will show you DS9 as well as some other image viewers, FITS image viewers. And FITS image viewers have all these capabilities of your actually changing the scaling, etc., so that you can see your image much more better, right? You'll see that if that is done, you can see various features, this thing. So Shrishti is asking me a question. um, does the count refer to the number of photons falling on that particular so it's not exactly the number of photons, it is a function of the number of photons. Okay, because actually what happens is, this is electronics, right? So for the number of photons which fall, you'll have what is called a read noise, and you will have what is called a gain, what is the power you will get on it. So it's not directly the number of photons, but it is proportional to the number of photons. Okay. Yeah, 2 power 16 comes as, there are screens. The screens you have 16-bit, 32-bit, 64-bit, right? So this is an earlier thing. If you had a 16-bit screen, the values which are possible on the system, the brightness values, the range, that is goes as 2 power 16. If you have a 32-bit machine, it goes as 2 power 32, right? So it depends upon whether you are, yeah. When to we decide the image size for our when to choose. Is there a way we decide the image size for our observation when to choose 16 or 18-bit? No, often that depends upon the system you have. That will define whether you're using 16-bit or 32-bit or whatever. There's another question by Keisha. Is the metadata part of the FITS file? Yes. So that's what I'm saying. The FITS format, it's all packaged together. The metadata as well as the image, they are part of the same file. So Alexei will show you in DS9 when he shows you after my talk that when you display a FITS file, you can also display the header of the FITS file. So the header of the FITS file is the one which has that has all the metadata. That means which telescope, what exposure, how long was the exposure, which filter, all that so it's packaged with the FITS file. So the FITS format is a format which lets you package all that together. Okay. Yeah. So in short, you'll see it in DS9 also. We use various methods to actually get our image better, to accentuate things. So here's an example. This is a star cluster I was working on, which is called NGC 281, right? Now what you're seeing over here is a composite image. Okay. Now, if you actually see, this is how this thing looks in optical. What you saw so many stars over here, right? You see all these stars over here. If you look in optical, you do not see them. Why? Because there's a lot of gas and dust in this region. So you can see this is all gas and dust, which absorbs all the starlight, and therefore you basically can't see the stars. So in optical, it looks like this. It looks pretty dark. But here is the image. We're using Spitzer telescope. So Spitzer is an infrared telescope. So if you see it in Spitzer, you can actually see so many more stars because extinction or the dust absorption is actually inversely proportional to wavelength. Therefore, what happens is infrared is long wavelengths, so extinction is lesser, right? So if you have a very dusty region, you may not see anything in optical, but you will be able to see it in infrared. Okay, so this is a Spitzer image where you can see everything. Now this square thing which you can see over here is Chandra. Chandra is an X-ray telescope. Okay, so the X-ray telescope you will also see images, and this one is also Spitzer data, which is the Spitzer cryo data. Okay, this is what we call this outside image is what is called the warm Spitzer, and this the cyan square, the rectangle is the what do you say, the cryo data. So actually Spitzer is an infrared telescope, so it had cryogenic technology to cool it. Okay, so that image is this one, which you can see with this big rectangle. But then later on Spitzer, the cryo fuel got over, and therefore Spitzer was used to then observe, not in all four bands, but to look, and that is what is called the warm Spitzer. The warm Spitzer is Spitzer without cryo. So the Spitzer without cryo is this big image. Spitzer with cryo is this rectangle, and the square over here is Chandra. So what you see is this is the Spitzer image, infrared. This is the Chandra image, and when we overlay these two together, we've exactly overlaid them. That's when we get this image. So this image which you're seeing is an artificially generated image by overlaying the images of Chandra and of Spitzer. So you overlaid the stars, and these purple sources are the X-ray sources. They are super bright sources, while the redder ones, the ones you can see behind, are the infrared sources, which are colder sources. So in that way, we actually, put all these, we kind of stack up astronomy images in different wavelengths and put it to actually accentuate. So for example, here, you can see that these purple ones are the hotter stars. This is the cluster. If you look up here, see, this is how it is in optical. You don't see any hot stars. In infrared, you see, this is infrared, and then in X-ray also you see it well. So now when I overlay it, you can clearly see where are the hot stars sitting. Okay. So in short, in astronomy, I am an optical astronomer, infrared astronomer too. So we do a lot of image processing. That means we process images so that we can see more features on the images, right? The other kind of data set you have, these are called spectra. What is a spectra? It is intensity versus wavelength. Okay. Now, why are spectra so important? Spectra are very important in astronomy because if you actually see, this is long wavelengths red, this is short wavelengths blue. You can see that there are certain black points over here. That means these are dips. These are what we call absorption lines. Okay. So that means if you have a certain element, right, that certain element will absorb light of certain wavelengths. And those wavelengths are signature wavelengths for those chemical elements, right? And therefore, if you get the spectra of this thing, what is the spectra? You have the light from the source, which you break it up into wavelengths. How do you break it up into wavelengths? The simplest is to use a prism, but actually we use grisms, we use diffraction gratings, we use various things to break up the lambdas. And then you can actually get these dips. So if you look at these are absorption spectra. These could also be white if there's excessive emission. Those are called emission spectra. And chemical elements have their signature wavelengths at which they do emission or absorption. So if you get a spectrum like this and you identify the spectral lines, emission or absorption lines, you can actually identify the chemical element which is doing that. So what happens is if you see the spectra of a certain source, you can say what is there on that source. If it's a star, you can say whether there's hydrogen or helium or calcium, whatever is the thing over there. So spectra, number one, gives you chemical abundance. The other thing spectra also gives you is it also gives you physical conditions. For example, if the gas is hot, you may have what is called thermal broadening. You may have Somebody asked about redshifts, right? What is a redshift? You have a galaxy which is at a certain distance away from us, right? And because the galaxy is at a certain distance away from us, by Hubble's law, we know that the galaxy is also moving away from us with a certain velocity, right? Now, that velocity is given by the Doppler shift. That means if that spectral line had some wavelength lambda, the lambda actually gets shifted. How much does it get shifted? Delta lambda by lambda is equal to V by C, right? Which will give you the redshift. So if I'm looking at the spectrum of a galaxy, I can actually, if I identify the spectral line, for example, I know Baba line 6530, and now I see my 6530 has been moved. It is now, I'm observing it, say, at 8,000 angstroms. So I know that it has shifted by a certain delta lambda, right? So once I measure that delta lambda, I can directly infer the redshift of that galaxy. So somebody was asking about redshift. So typically, if you want redshift data, you basically use spectral data because your spectral line is getting shifted, right? And you measure the shift in the spectral line, and that will give you the redshift of that galaxy. So, in short, spectra are very useful. Chemical composition, physical condition, redshift, various factors are found out from the spectra, right? Which is a very important source. The next thing is what I want to talk about is what we call data cubes. Now, imagine, for example, you took an image of a certain galaxy, say in a green filter, which is this, right? And then I take an image of the same galaxy in a blue filter, in a red filter, in a yellow filter, in different colors, right? So what we do in astronomy is we stack them up together, right? We put them all together. So this is your image, right? And along this, you are moving wavelengths. So think of this like a loaf of bread where you have slices, right? So each slice is an image of a galaxy, for example. And each slice basically differs in wavelengths. So for example, what you have in blue is at shorter wavelengths, what you have in red is at longer wavelengths. So you're looking at the same object through different wavelengths. So if I look at it from here, I can actually see the whole object in a certain wavelength. But if I take a slice like this, right, I can actually, supposing this object and I take a slice inside, I can actually look at this object, the brightness of this object in different wavelengths, which in principle is the spectrum of the object, right? So what happens is these are what are called data cubes. So you have a data cube, which is an image, which you have it put over here. Okay. So that's it. Data can be in the form of a catalog. We will talk later about virtual observatory. So there's a certain format in which we put this tabular data, which is called the VO table format, VOT. It could also be as a CSV file or other formats, but typically it's a tabular format, and you may then work on the tables. You could also have what is called time series data. That means I told you you have time on x-axis, you have brightness on y-axis, and this is your time and your brightness is varying with time. This is called time series data. How do you visualize this? Alexei will show you DS9, which stands for Deep Space Nine. There's also something called the FITS viewer, the Sky View, there are other things with which you can look at images. Catalogs are often seen with something called TopCat, and programming languages are also used for analysis. Python is the most used one specifically because Python has various modules and libraries specifically for astronomy. So there's something called AstroPy, there's something called AstroQuery, there is also called PyVO. So there are various Python modules and libraries which have been built specifically for astronomy. The metadata, like I told you, is present with the data. So I need to hurry. So what are astronomy archives? So astronomy archive is basically systematic information about the sky is called an astronomy archive. Now data has been archived since ages. The earliest archive we have is Hipparchus. And what he did is he looked at about 850 stars and he defined a scale called the magnitude scale. So a first magnitude scale was the most important star, first degree. A sixth magnitude star is the sixth most important, so sixth degree of importance. So therefore the magnitude scale is a reverse scale where a first magnitude star is brighter than a sixth magnitude star, right? So with our naked eyes, this is obviously way before the telescope, and therefore 1 to 6 magnitudes are the brightest we can see with our naked eyes. We cannot see beyond this with our naked eyes. Another very important observer was Tycho Brahe, who he observed planets, naked eye planets, as a function of time. So he was basically marking out the orbits, for example, of Mars, all with time. And the first person to actually use archival data in principle is Kepler, because Kepler was actually formulating his laws for planetary motion. So he was actually testing it a lot with Mars, right? And Tycho Brahe's data was available for Mars, Jupiter, etc. So what he was actually doing is he was actually using Tycho Brahe's data, which actually mapped the position of these planets in the sky, to actually define planetary orbits, right? So he actually formulated Kepler's laws of motion. So you can say that Kepler is the first example of archival data giving you science, good science. There were various other catalogs also made by people. You can have a look at those. So one of the earliest data samples is the Palomar Sky Survey. So there was the Palomar Observatory, and at that time, what was done is photographic plates. These are huge plates, which were 14 inches square photographic plates. Each plate covered about 36 square degrees of the sky, and it was used to actually expose it and get images. Okay. Now, obviously, this is very cumbersome having photographic plates like that. So, in the 90s, they digitized these plates and they called this the Digital Palomar Sky Survey. So, the DPOS survey is the Palomar Sky Survey. And basically, this whole thing has happened because of technology. In astronomy, technology has played a very important role. We had charge coupled devices, digital cameras. These are what we call linear devices. That means the brightness will increase as a linear function. And this is a typical CCD, looks like this. And therefore, the amount of data which is now available in astronomy is colossal. Okay, it is way more than the number of astronomers we have. And therefore, we have what are called citizen science projects, where actually citizens who are non-astronomers are also encouraged to look at astronomy data. Because the problem is there's so much of data that the number of astronomers are not enough to look at all this data. So we would like people to actually, actually have a look at at the data to actually look for it. So there's a question by Sampreet Das. Are those redshift surveys done for one galaxy at a time or all galaxies from a whole chunk of a sky being observed? So thank you, that's a good question. So typically, yes, you would do one galaxy at a time, but nowadays there is a technique which is used in telescopes, which is called integral field spectroscopy. So for example, if I have a cluster of galaxies, I can actually collect the light from each of the galaxies using optical fibers, so that each of those galaxy sources will actually, I can find out a spectra for each of this. This has been a major revolution in astronomy spectroscopy, because the problem is when you're doing spectroscopy, you need to observe for a very long period. Your exposure time have to be 1 hour, 2 hours, etc. Because you are typically catching photons only in a small wavelength range. So if you're looking at a galaxy far away and you want to do spectroscopy of it, you will need to observe it for like 1, 2, 3 hours, right? Which is obviously very expensive in terms of telescope time. So earlier, this is how it was done. Nowadays, we have what is called integral field spectroscopy. That means in the image, supposing you have 1,000 galaxies, it's a cluster of galaxies. From each of the points, we use optical fibers to guide the light and get spectra at the same time. So at the same time, you can get it for a whole cluster of galaxies. So in today's times, we get it for a whole cluster of galaxies. We are using CCDs, and we get a large number of this thing. So technology has been hand in hand. Also, like I told you, Astronomy Archives is the true spirit of science, because the data is available to everyone. For a certain period, sometimes the data could be with proprietary period only, instrument groups, etc. But otherwise, for a bulk of time, there's a whole lot of other data which is available for everybody to use. And because there's so much of it, there's also citizen science projects where even non-astronomers are encouraged to use the data. So what are the data archives? One of the important one is called Vizier. Vizier basically has the data of published papers. So if you've, supposing I observed a cluster, I published the paper on that. The data I used can be put up on Vizier. So the idea being that anybody else who wants to have a look at my data can use it, get downloaded from Vizier. Sometimes this is very useful also because data analysis techniques vary. For example, if you're looking at gravitational waves, there may be people who may analyze the data using different techniques. So if I have published a paper using my technique, right? Now I keep the data available to everybody. So if you want to use another technique, you can use that and compare that to mine. There was also a big controversy about phosphine on Venus. So, for example, the data was made available to the community. So, we had other groups who were analyzing the same data and getting different results. And therefore, there was a constant, talk between different groups because they were using the same data set and getting different results. So in science, what we need is transparency. That means if you and me use the same data set, in principle, we should get the same results. So that can be tested by using Vizier. Simbad is an astronomical data which gives you basic data for any object in the sky. You can actually find it. If it's an extragalactic, it's in NED, otherwise it's in Simbad. The Sloan Digital Sky Survey, which is surveyed about a quarter of the sky. 2 Sky Survey is a near-infrared survey, all the sky. ESO data archive is ESO observational data. Then a very important archive is the MUST archive, the Multi-Mission Archive at Space Telescope Science Institute. This basically has all NASA space telescopes. So it has Hubble, James Webb, Kepler, TESS, GALEX. It also has Gaia, though Gaia is an ESA telescope, European Space Agency, but they work in tandem with them, and therefore even as they're the MUST site. So the MUST site is a very important site for you to actually use to get space telescope data. There's also the IPAC database, which is NASA's infrared submillimeter wave. Then there's the Hubble Legacy Archive. There are various archives. You can actually find them on the net. So this is the Hubble MUST. So the MUST archive, it has Hubble, James Webb, TESS. K2 is Kepler data. You can get all this data from these websites and you can use that and analyze it. There is the Gaia data, which is also available. Either you can get it from the ESA website, European Space Agency website, or you can get it even from the, from the NASA website, from the MUST website. And there are more than one website so you can get the data for Gaia. In India, we have what is called the GMRT, the Giant Meter Radio Telescope, which is a 30-dish telescope. It's a state-of-the-art telescope. So this is an example of ground-based telescopes where you can actually look for proposals of people. And like I told you, for a certain period, the data is proprietary data. It's only owned by the person who gave the proposal to observe it. But once the proprietary data period is over, the data is available to anybody in the community. So you can also look at the GMRT online archive. This would apply, for example, even for the ALMA archive. If you want to use ALMA data, maybe you, to first of all write a proposal, etc., is difficult. So it's good to actually use some of the archival data. And if you can get some results, see the analysis, see how do you analyze it, what do you do, and you can use that to justify a proposal of observations that you may want with ALMA. Okay, so here, so what happens is ground-based telescopes also can be accessed like this with archives. Chandra is a space-based telescope which basically looks in the X-ray. So you can go to the Chandra website, and in the Chandra website, you will actually see there's a point source catalog and there are various things. In all these things, I should inform you all that there are always help desks. So because the problem is that each telescope has its own specialities, special things about it. So even if you have used the NASA website, you may have a problem using the Chandra website, right? So all of these websites have help desks. So if you have any queries, you can always write to the help desk and they will definitely be happy to answer your questions. There's another question, Anupama, who's asked me again about the redshift is analyzed. So the redshift is analyzed, Anupa, basically using what is called the Doppler shift. Okay, what is the Doppler shift? That if a source is moving with a certain velocity, then it's if there's light coming out from it, it will get shifted. So if it is moving away from us, it goes to longer wavelengths, which we call redshift. If it's moving towards us, it goes to shorter wavelengths, which is called blue shift, right? So what happens is when you're looking at the spectrum of a galaxy, supposing you identify the spectral lines, you will notice that the same spectral lines are slightly shifted, okay? And they'll typically be shifted to the longer wavelength because they are red shifted. So from the Hubble's law of expansion of the universe, we know that galaxies, as they are further away from us, they seem to be moving away at larger speeds. So if we measure the speed, we can actually measure the distance to the galaxy, which is nothing but the redshift. So the redshift is found out using the spectrum of a galaxy. Okay. So another data set is the SDSS, the Sloan Digital Sky Survey. This is mapped about 1/4 of the sky. So we have what's called virtual observatory, which is a movement to actually synthesize the efforts of all these telescopes, okay? Creating what is called a virtual observatory, which is a multi-wavelength digital sky that can be searched, visualized, and analyzed in new innovative ways. So what is done in virtual observatory? We have what are called standards. That means all images, for example, should be put in the FITS format, right? You have data put in certain formats. Metadata should be put in a certain format. Otherwise, the problem is in all these different data sets, everything is written in a different way, right? And therefore, what is done is virtual observatory set up their standards so that all the data is put in a standard form, so that in a standard format, people can use it. And supposing even I am an optical astronomer, but I want to use X-ray data, I should be in a position to use X-ray data because it is, in a standard form. So I can actually get the things I want in a standard way. So that is the virtual observatory. So virtual observatory is basically a framework of data archives, software providers, data centers, with which you can access data. Okay. Now it's a whole movement which happened in all around the world. You had about 23 different VO projects all over the world. You can see this is VO India. This is Eurovio. This is the German one called Gavo. This is the French one. This is the Japanese one. Then you have the Australian one. So you have various countries which were part of the VO project, and they developed tools, etc., to analyze data. So Alexei will talk to you about it, so I won't talk to you about it. But I'll wind up with this. So basically, virtual observatory are, we'll hopefully talk a little bit more about it. Alexei will talk to you more about it, where you'll see that there are different tools with which we can access the images, the spectrum, the various data sources which we actually get in from the astronomy data archives, and we can use them to actually get the data. Okay. So the important thing is to first define what is your science case. What is it that you want to study? For example, do you want to study exoplanets, or do you want to study galaxies or stars, or what are the objects you're basically looking for? What is the kind of science case you're studying, right? Based on that, look for data sets where you can find the data which you want and study how to analyze it. So a very simple method would be if you can actually find papers. Supposing you want to do Kepler data, right? Find a paper which has used Kepler data, right? And you will see in the paper the analysis techniques which they have used, and you can actually use those analysis techniques. In some papers, sometimes they even give you the notebooks that they've used, so you can actually use their notebooks, or you actually write your own notebooks and learn how to analyze the data, so that you can then use that for your capstone project. So first of all, define the area you want, look for papers which have actually done that, then you see how the papers have done the analysis, right? And then see how you can use it, first of all for the source that they have done it, and then for some other sources, right? And obviously all of us are there to help you, so in case you have questions, doubts, you're most welcome to ask questions and come up with it. So thank you very much. I will end with this, and I will hand it over to Alexei, who will take the next hour. Yeah, I don't see any more. I think most of the questions I answered while I was talking, so I don't see any new questions. If there are new questions you can ask. Otherwise, Alexei, you can take over. Thank you very much. Thank you. Thanks everyone for your appreciation. Thank you very much for all your claps. Thanks a lot. Alexei.
Hello, everyone. Hello, Priya.
Hey.
Thank you for your presentation. So, okay, let me share my screen. So, okay, I hope you can see it.
Yes, yes, it's all fine. It's all good.
Thank you. So, in this part of the course, we will briefly discuss how to fit files are used in practical astronomy work. We are going to study We are not going to study full FITS standard in all technical details. Instead of that, we will focus on the basic operations that an astronomy usually needs when starting to work with observational data. We will see how to open a FITS file, how to check its internal structure, how to read a header, how to access actual data stored inside file. We will also look at a simple visualization of its images and at how to use world coordinate system information, which connects image pixels with coordinates on the sky, which is very important to understand what we actually see on our current image, which we will draw. So only a minimal understanding of Python and AstroPy is all you need. Main goal is to understand general logic of FITS file. That actually FITS file is not just an image, but a structured scientific data file containing both data and metadata. So let's move next. Okay. Okay. Here you can see image of whole sky by 2MASS survey. Of course, modern astronomy relies on a large sky surveys. Such surveys collect data for large areas of the sky, often in several wavelength ranges. As a result, astronomers can study not only individual objects, but also large-scale structures of many objects, such things. Okay. Usually, survey images and catalogs are now a standard I think standard point for many research tasks. So before planning new observations, it is usually necessary to check where the object or region has already been observed by existing surveys. This move can save telescope time and can also provide important context for your new observations or your plans for observing some objects. So the important point that survey data are not only pictures, they only include collaborated images, source catalogs, spectra, time series data, and I guess many other types of information. So most of the modern astronomical surveys provide online access to their data, of course. And in many cases, we do not need to download original files immediately. We can first inspect the object or by Simbat or region by Ladin. So by using online services such Skyview, of course Simbat, of course Vizir, IPAC, and of course Aladdin, or maybe even survey's own archive. Almost every survey, big survey, have own archive, so you can usually check it, or use Vizir, where you can find almost any surveys, I guess. So this is often sufficient for a quick check, so we can see where the object is visible, compare different wavelength bands, check coordinates, maybe find some catalog measurements. And sometimes online tools are very useful for the first stage of our data exploration, of our data science. But if we need a quantitative analysis, custom measurements maybe we want to make our own image processing, photometry, spectroscopy, or maybe something else. In that way, online visualization is not enough, of course. In such case, we usually download original data files. So in astronomy, of course, these files are very often provided in feeds format. So, Priya already mentioned what feeds actually it's feeds stands for flexible image transport system. It is a standard format used for storing and exchanging astronomical data. Also, word image is part of the name, but feeds is not limited to ordinary images. Feeds file, of course, can store images, spectra, tables, data cubes, and other structured datasets like radio spectra, radio maps, even optical and infrared interferometry data. But of course, in such way, for optical and infrared interferometry, we usually use another way of feeds standard. It's called OI optical interferometry feeds, OI feeds. So one of the main advantages of feeds is that it stores data together with metadata. This means that the file may contain not only pixel values, but also information about the observation, like exposure time, coordinates, telescope name, instrument, name of observer, of course, detector information, filter, calibration state, and processing history, of course. So this is why feeds is still widely used. So of course, format was standardized in in okay, sorry, it's okay, slides right. Okay, of course, okay. So it's not just a container for numbers; it's a scientific data format designed to preserve the observational context of the data. And of course, today we have a lot of libraries for working with feeds files, and of course, a lot of them in Python. So let's move next. Very useful slide, I guess, for you. I hope you will understand basics about feeds file structure. So feeds file should not be understood as a simple image file, as I mentioned before. It's better to think of it as a scientific container that stores both data and information needed to analyze this data correctly. So the basic structural element of a feeds file is a header data unit, or HDU. Yes. So we have a file. Every file have a HDU, and actually a primary HDU. And of course, feeds file may contain one HDU or several HDUs. Soon we will see. Each HDU represents one logical block of information. For example, one HDU header data unit may contain an image, another may contain a table, table with some model results or additional calibration data. So, of course, each HDU consists of two main parts, a header and the data section. Header describes what is stored in a data section. It is written as a list of keywords. So we have a list of keywords. Each keyword usually has a name and a value, and sometimes comment explaining its meaning. So these keywords may describe the observation, instrument, detector, coordinate system, and other things, as I mentioned before. What about actually the data section here? Of course, data section contains the actual scientific data. It's in the simple case, this may be an image, just image array, a numerical array representing a CCD image or maybe another detector frame. But feeds is not limited to one-dimensional images. It can also store spectra, data cubes, multi-dimensional arrays, or other numerical data sets. So these arrays may use different numerical formats, such as integer, floating point, or double precision values. So it's always depending on requirements, accuracy, and dynamic range. So feeds file may contain transforming extensions. An extension is an additional HDU that follows feed standard and allows feeds file to store more than just usual data. And this is why usually you can find not only images in feeds file, but tables. So yes, another important type of feeds data is a table. Tables store information in rows and columns, of course, and are widely used for catalogs, maybe source lists, spectral measurements, observation logs, some information from modeling, parameters of modeling, and so on. Of course, feeds tables may store in usual ASCII tables, which of course are more human readable, or as binary tables, which are more compact and more suitable for big data, but not so human readable, of course. So main idea is that feeds file is a structured scientific file. To work with it correctly, we need to know not only where the data are stored, but also how to how header describes our data, our units, coordinates, of course, world coordinate system, very important to images of the night sky, calibration, and so on. Okay, so main idea of all these slides about feeds standard is remember header data unit, HDU. It's a header plus data, and one HDU is used for each data block. So in one feeds file, maybe a lot of HDU. So be careful when you're opening feeds file. You need to check what actually in this file. Maybe not only images, maybe some tables. So let's move on. Here you can see a typical header. Of course, we can see keyword and value pairs. For example, date or for example, exposure time in seconds. So we have a keyword, we have a value, and in comments you can see actually units of value. So exposure time in seconds, of course. Maybe some coordinates, like right ascension and declination, but usually it's not so accurate. So in modern astronomy, become a standard to use astrometry.net library to make a better, or I mean best, world coordinate system in header. So we will see it soon. So of course, all keyword names and values are written as in ASCII standard. Header may also contain information about astrometric grid, wavelength, flux calibration, and other a lot of parameters. So actually, in practice, I think reading the header is one of the most important steps. So before analyzing the data, we need to know actually what kind of data we are working with and what units are used, where image is calibrated, where an image raw, and how pixels actually correspond to physical or celestial coordinates. So we need a software to actually open our feeds files. As I mentioned before, a lot of programming language support feeds file handling, like of course C++, but now we all love Python. So we will talk about old-fashioned apps and about Python, of course. So historically, one of the most important software systems for working with optical astronomical data, of course, was IRF, Image Reduction Analysis Facility. It was used for image reduction, photometry, spectroscopy, and many other things. It's pretty old, but still powerful and useful, I can say. So, of course, for this course, or maybe even every modern course, we don't need to study IRF. It's enough to know that IRF exists and played a major role in development of astronomical data reduction workflows. So many classical procedures used in astronomy were, uh, were implemented and were implemented like IRF style. Now we have actually a PyRF It's IREF in Python, but I don't like it, and maybe I will not recommend to use it. But as you wish. So of course today all pipelines and workflows moving to Python. Many ideas from IREF and ideas that were common in IREF are now available in Python libraries, of course, such as AstroPy, PhotoUtils, ccdproc, and specutils, spec, reduce, and other. So, of course, this makes Python more comfortable and maybe even more user-friendly to make raw files reduction, maybe some analysis, and maybe even publication quality workflows, I guess. So let's move next. Oh, okay. I even made a slide to show how actually IREF looks like. And main feature of IREF is very not user-friendly. Nowadays, we don't like such apps. We again, we love Python, so I think maybe your astronomy future will be with Python. So, but which classical tools we still can use today? Of course, DS9 and Fits Viewer. It's tools for opening and inspecting Fits files. So they are useful because they allow us to look at the data before writing detailed analysis code, because you need time to make some code in Python. I know you can use modern LLMs like DeepSeek or ChatGPT. They can make code very fast by your prompt. But maybe it's still useful to use such old tools. So DS9 is mainly an astronomical image viewer. It is used to display FITS images. You can change contrast and scaling, of course, inspect coordinates, overlay regions, check world coordinate system information. For example, before running some pipelines, maybe even in IREF, it is useful to open image in DS9 and check where object is visible. Maybe no actually scientific information in your image, only noise. So DS9 fast and useful. We will see soon. We will see. Fits viewer or FIV. It's mainly used to inspect an internal structure of its files. Of course, FIV can open images, but it's mostly for tables. Yes. So if you will meet and you know this file contains some astronomical tables, it's much more fast to just open FIV and open your table. Remember that. So, what about modern tools we can use? Of course, Carta. Okay, Cube analysis and rendering tool for astronomy. Carta represents, I think, more modern approach to visualizing astronomical data. It is especially important for large images and multi-dimensional data cubes, which we call big data. Big data comes to astronomy with every day, bigger. For example, in radio astronomy, a lot of big data nowadays, I guess. A key feature of Carta, it's a client-server architecture. This means that large data files can remain on a powerful server, maybe even NVIDIA AI, of course, GPUs, while user just interact with them through a browser or graphical interface. Yes, this is important because modern fits cubes can be very large, like maybe even hundreds of gigabytes. In some way, maybe even thousands of gigabytes. It's not a good idea to download it to your laptop because SSDs nowadays are very expensive, you know. So it's better to process your data on a server. So Carta can do things like DS9 and even much more. So I guess you can start to use it. I hope you will use it actually, because modern astronomy still will be all about big data. So what about Python? Of course, AstroPy. Uh, AstroPy can help you to read, write, and modifying some feeds files. Of course, you can use units, coordinates, word coordinate system, tables, and much more features of AstroPy. I mentioned only features to feeds handling. Phototools can help you with source detection, aperture photometry, point spread function photometry, and background estimation. A lot of things in phototools come from IRF. CCD proc, CCD about CCD calibration, like bias, dark, flat field correction, and image combination. Of course, you can do in simple way. You can do all these calibrations in AstroPy, but CCD proc can be useful too. Of course, AstroQuery. From AstroQuery, you can access to astronomical catalogs and archives from Python. So usually people from AstroQuery accessing to, for example, Gaia tables or maybe some photometry tables. But remember, by using AstroQuery, you can access not only the data tables, but even to feeds files, with images. Remember that. What about spectros? SpecUtils, spectral and data analysis and line measurements. Very useful. Of course, a lot of things, a lot of features comes from IRF. And to reduce raw spectra, SpecReduce flexible toolset for extracting spectrum and spectral image. So you can use it. And I added this slide because nowadays, of course, modern like things like ChatGPT or DeepSeek can often write working Python code for simple AstroPy tasks. And this is a secret, not only for simple tasks, but of course, opening feeds files, reading headers, plotting data, and plotting data, I will say again, because sometimes we all hate matplotlib, and now we can ask LLMs by prompting, just to plot some beautiful plot. And actually, LLMs will do that. Sometimes quality of such code seems to be improving by LLM's company, and number of errors, not so much errors today. But remember, now, of course, students, more and more students use AI tools when they're writing code. No, but remember, working code is not always correct, scientifically correct code. So not always scientifically correct code. It may run successfully, looks good, but it still use wrong data, wrong units, maybe wrong coordinates, or just LM can't understand structure of difficult, some difficult, for example, feeds file. So how much you use AI assistance in this code is fully your decision. In my experience, it's a stupid thing to say student to don't use LLMs or ChatGPT or DeepSeek, because they still will use it. But remember, you are responsible for checking your results. Because sometimes my students tells me like, "Oh, this is DeepSeek error. This is not my error." Don't be like them. So your code, your responsibility. Remember. So let's see some practical, interesting things. Let me move. Okay. Simple way to find some images. Aladdin. Maybe RCA. Let's find it. Oh, it's Erasita. Let's see some usual thing. Thomas survey. So you can download it, and you can see even in color, because Aladdin already use color in JHK. Aladdin have a online version. Usually I love it when I need to see fast something about object, and desktop version can be useful too. Here you can see some other service, for example. Oh, no data in Spitzer. So always, yes, you can see your data in always, and you can see blooming. So RC ray too bright, start to observe by wise. So, but what if you, of course, want to download some feeds file? As I know, actually, some way you can download directly from Aladdin API. Maybe I'm lying, but if I remember right, you can do that. I never did that. So another online thing which I love, it's IRSA or IPA from IPAC, where you can find images from a lot of surveys. For example, WISE. So let's find RCRA here. No set for us today. So, of course, and we can go to IRSA viewer. It's already open here, but let's go. Just wait. So yes, you can see Vice filters here, but what about real images from feeds file? We can always click here, RCRA, which survey interested we, of course, Vice, all Vice. Let's search. And here Russian thread connection, sorry. That was a big mistake to close. Oh, okay. We can see, still we can see a blooming. We can see 4 filters, Vice 1, Vice 2, Vice 3, and Vice 4, of course. And here we can download it. I already did this, but let's download again. Just maybe Vice 4. And click here, save. Okay, you can save even like PNG file. Funny thing. Okay, save this file. I already installed the DS9, of course. So let me show you original. So original site of, it's not really original, but okay. DS9, you can download it. Of course, for Linux, macOS, Windows, even Source, if you want to compile that. Let's just open. And nothing. Okay, finally. I hope you can see it. DS9 window. So our image from Vice, which we download right now from IPAC, IRSA. IRSA, it's Infrared Science Archive. So it mostly contains infrared surveys, of course. So you can see header of Vice feeds file. So usual data here. Of course, we have a world coordinate system header path. It's we have it, so we can see not only here, not only value and physical coordinates like pixels. We can see actual right ascension and declination of every pixel, which can be very useful to inspect some images. Here we can see value nan, so it's because it's blooming. CCD was full of pixels or of photons. But here we have a world coordinate system. But if we will open file without, let me open. Okay, open is easy. Find file is not so easy. Oh, I finally found. Just the raw data from our Ural Federal University telescope. Let's open the header. Okay, we can find even CCD temperature, coordinates of our observatory, name of our observatory, some other things, object name, simple coordinates. As you can see, it's hours, minutes, seconds, not degrees, for example. So be careful. Information about seeing, other useful things, but you can see any information about world coordinate system because there are no WCS information because we don't need it. We can just use astrometry net. We don't have time to talk about astrometry.net, but I think this is most useful thing in practical astronomical observations of big fields, not only one star of course. So you can just upload your image. Let's upload it. And we will wait. Of course, I did it before, so let's open it. Just do not wait, because we don't wait too much. Oh, okay. Okay, it's working. So as you can see, no coordinates from world coordinate system here. Just nothing. Only pixels. Let me open. Okay, I deleted. So you can hear, or you can see here, finally. As you can see, astrometry.net even detect stars here. So if we will download this image file, you just will have a world coordinate system. So you can inspect actually celestial coordinates of every pixel. And actually you need it only if you have only one star on a picture. And usually you know which star is it. So move on. But what if you find some table data in your feeds file? As I mentioned before, we can use FV, feeds viewer. So let's find it on my PC. So let's start. Here and here. So, of course, you can actually open image such way. You can see a header, of course. For example, you can type FWHM 4. Not so good. You can inspect header 2. It's such good as DS9, but image. What about image? Of course, image. Feeds viewer or DS9. And DS9 image. Let me open again. Here. I think it's pretty the same, but DS9 more powerful, a bit more features, but DS9 can't open tables. If you will try to open a table with DS9, you can see such thing. very useful. So, what about tables? Okay, we just open file, of course, Flux. Here you can see actually fits with tables, and you can see six header data unit, or HDU, 6 HDUs. Each one have a header, so we can open. It's not so big for images, of course. Just distance of our models, for example, how many wavelengths we have, and how many number of apertures. So we can see all our table, just model names, for example, 10,000. Maybe we want to see some spectral info. Okay, 2 columns with frequency and wavelength. 200, yes, 2 columns and 200 rows. As you can see, here we have a cube data, such values, which we can try to make image, but this is not a good idea actually. Okay, let's don't do that. So table. Here we have a lot of slides. So for example, 5. Yes, and we can see actually table with fluxes on every wavelength. So of course, Fits Viewer, it's very useful to very fast access to table data from Fits files. I think you already understand about this one. What about scale? Not about pixel scale, like brightness and contrast. So here, min-max or z-scale, for example, from here, if we'll choose z-scale, picture will give much more information about stars for us. Here, we can, if I remember right, of course, for example, square root or such one. You can always rescale with your own parameters. So pretty simple to use. So let's go to Python, I guess, finally. Let me find here. So as always, we need to import a lot of libraries. Of course, matplotlib, how we can live without matplotlib. Fits files to work with world coordinate system. And some tricky visualization tools. We will need to make a z-scale, like in DS9, because we all love it. And of course, AstroPy units. So let's open our file. Of course, not linear programming, sorry. And one feature about Fits file open. So if you still don't install Carta or don't still have a very powerful server like me, I don't have one, you can use a tricky way to open a big Fits file. Maybe you don't have a lot of memory in your laptop, so you always can use a memmap optional argument in open So just use map when you don't want to upload all file to your RAM. So remember, if your laptop not so powerful, you can always use it. So let's find out what we actually have in our feeds file. So as you can see, only one header. If you will open feeds viewer, the same here. Yes, just header, image, and even our table. But what table? Our image we can show like that, like just table, because every image is just array. Yes, remember. So the same in Python. It's very easy, I guess. Not much time, as I said before. So let's access actually data and header. Here, now we can see image shape by this by this row, and data type. So our data, just a NumPy array. So when AstroPy reading science data from your image feeds file, it convert just to two-dimensional NumPy array. You can see shape and you can see type, int in our situation. But what about header? Okay, we can see full header. Great. We can actually make some changes in header by using AstroPy feeds handling. Maybe you need to make a new header for your new file. So it's easy. We don't have time to I don't have time to show it, but remember, it's easy. It's very easy. So I think you can handle it without me, without my help. So, but here we can't see any information about world coordinate system. Yes. So I download a new image from Astrometry.net. If we will go to result page, here we have a new image file, new image feeds, which contains old header plus new header, which contains world coordinate system. Of course, we can download only world coordinate system feeds file. Maybe it's useful for someone. As you can see, astrometry.net even detect some objects here. Very useful, maybe not. Okay, let's go back to our file. So header. Okay, if we open new image file, you can see a header, but now we have a lot of comments. These comments come from Astrometry.net calibration, but if you will use your mouse, we can see now we have a world coordinate system header in world coordinate system information in our header. So great. Now we can use it. For example, to make celestial axis for our image. Let's do. So world coordinate system keywords, you can see it here. Actually, this is a CD matrix elements. It describes transformation from pixel to sky coordinates. We need it. From them, we can calculate, for example, pixel scale or field of view of whole our telescope. Let's do that fast. Okay, our pixel scale. We calculate in old fashion. Of course, we don't need it. We can use a function from world coordinate system AstroPy. Okay, in degrees. Let's use magic of AstroPy units. Okay, the same result here and here. Great. Let's make im show of our image. Okay, it's not so great. Contrast and brightness not good. And we don't have actually axis. It's just pixels. We still can use it, but we want a beautiful publicly available picture, of course. So we can use variable normalization, image normalize. We can use interval for z-scale and our data, which is actually contains our image array, numpy image data array. So let's do. And a bit more complicated matplotlib code to make an image. So main thing here, projection of axis. Here, we made it before. Here. So we read word coordinate system from header. So now our axis is available to imshow to matplotlib. So let's make our image. And of course, normalization we can apply here. Apply astronomical image normalization. So our image now have a great axis and good brightness. But remember, we have raw data, so actually our pixels is just some analog digital units, means nothing without standard stars. Remember that. Maybe we want some much more beautiful plasma, if I remember right. Yes, something like that. So you can play with scale color map, it, maybe to make some really beautiful images. Why not? What about RGB images? So for RGB images, we actually need free pictures of our sky in different filters. For example, filters GRI, we can download it and we can still make imshow. And maybe you will ask, what is origin lower? We needed it because another way our image will be always up down. Okay, or I forgot how to say it. So our our axis will be not so good. So let's make image not so bright. Don't have this image have a not good not good brightness. So of course we can adjust it. Let's make adjustment. Okay, now it's like you can print it to poster. Looks great. Another one feature of this file which I forgot to say to you. HDU, but why L is here? Because it's HDU list, header data unit list, Python list. I mean, not like Python list, but still. So it's a table of header data units which our FIS file contains. Remember, that's why we need a 0 here, because we have only one. So in Python, it's a 0. If you will have much more header data unit, you will need not only 0, of course. So let's move next. What if we have our data fits file with tables? The same, we are opening file the same way. Of course, just file name, HDU list fits open, and let's see. Oh, okay. As we can see, it's in fits viewer before. Our fits file contains 6 header data units. So 1 primary and usual ones. Of course, we can access every header like this. Of course, we have a object to class, and in such way we can show it, for example. So we can see spectral info data. We extract our table, which have, as you remember, wavelengths and frequencies. As always, it's just a NumPy array. Okay, it's NumPy record, but it's like NumPy array, these features, of course. Maybe you want to see some values. As you remember, it's a cube. So, of course, we have a NumPy array such shape, cube shape, yes. 100 by 1 axis, 20 and 200 is our data. So we have not much time. Our lecture already almost finished. So maybe you have some questions. Let me open a Zoom. If I will find it. Of course. Okay. Is there any particular application or software required to support these feeds images in our computers? Maybe I don't understand the question, but you can use any feeds file processing app. Actually, here we have no, we have nothing. Maybe no. Okay, it's must be in presentation. Here. Actual list of feeds image viewers. So almost every software. We have even something new like GS9. I don't know if I love it or not. Next generation astronomical visualization. It can work in web browser, which may be very comfortable for you, maybe not. So you can use whatever you want. Do astronomy researchers use tools like Serial or PixInsight to work with feeds, or tools like DS9 are primary tools used? Okay, good question. If you need just to inspect image fast to understand you actually have a science object on your image or not, you can use DS9. It's for a lot of astronomers, it's a primary tool. But even IRF for a lot of astronomers still a primary powerful tool to reduce your images, to make photometry, to make a spectral reduce. So I never used serial or Pixel site, but if it works good, maybe you can just use it. So Lazarus type, I don't understand. Oh, okay, sorry. Maybe my Russian accent is very very bad. I understand. Sorry. Maybe just the presentation will help you. I think this is all questions I can see. So thank you for listening me for a whole hour. I hope this information will help you in your astronomy future. Remember, I didn't tell you about AstroQuery, but as you can see, AstroQuery is a very powerful tool. It can, as I mentioned before, it can do IRSA queries. This one, IRSA, yes. It can do Simbad queries, Vizier queries, even James Webb queries. Yes, here. To James Webb archive, I mean. A lot of people now use it, I know, and usually they love it. So I think in your capstone projects, in some way you will use AstroQuery to download your data, or as you can see, you just can download it from IRSA data archive or some other archives which you prefer. Okay, thank you. So,
Hello. All right. Thank you very
Daniel,
much. Yeah, thank
thank
you very much, Alexei. Thank you for the participant, and thanks to Priya for starting the section earlier, and then Alexei finishing up. Please, guys, what I'm going to advise you is that you need to take your time, go through the materials, and consult the links that even things that Alexei have shared. If you can, the softwares that were mentioned, they are totally free. DS9 is free to download. Even though Alexei mentioned Kata on a light note, you can also download it. There are a couple of ways to download astronomy images. You can do that and try them out. But most important thing is get your hands dirty. This is the week where you will be able to search for astronomy data sets, particularly from Visia, and also how to use Python API to download them for free to as many as possible. Visia contains tons of catalog that you can explore, mostly tabular data. Many of them are surveys from different telescopes representing different objects from exoplanets to stars to galaxies to large-scale structures and the rest. So please do enjoy the rest of your day. And also, there's a link. If you go to the GitHub repo for those asking for capstone project, there is a link in the GitHub repo that already describes what is expected of you in your for your capstone project and how you should present them. But please check it out. And I think this is where we'll end the section for tonight. Thank you very much.
Okay, thank you. Thank you, Daniel. Thank you, everyone.
Oh, sorry, I see Harrison's hand up. Harrison, I don't know if you have a question.
Yes, some
Yeah.
hands.
Hello, good evening.
Yeah, go ahead.
Yeah, sorry I joined late, and first of all, I just want to know if the recording for this session will be available, because I
It
think
is
this.
available. This is streaming live on YouTube. So if you go to the YouTube Bricks Astronomy page, you see that every section is streamed on YouTube. So if we end the meeting now, you can go to YouTube and access it there.
Okay, so also you talked about the links he shared. I don't know if he shared some links in the
So
comment
if you go
section.
to the GitHub repo,
Okay.
if you go to the GitHub repo, you will see a link that talks about the Capstone project. I think in the second section of this, in the second week of this school, we talked about it. The link was shared. If you go there, you will see, if you see the project folder, you will see a link on capstone.md. So the things that is required is already there. Let me share it again one more time before I end this meeting.
Yeah. What I mean, the links for the DS9 and like most of the things Alexis shared today, like the links. That's what I mean. What I
No,
mean.
the software that were mentioned, if you watch the video on YouTube, you will see them. Just a search on Google will take you to where you can download them.
Actually, I
Alright.
can send a presentation to Daniel.
Yeah,
Daniel,
you can
yes,
send. Yeah, you can
me.
send it, and it will add it to the list. But for every
Yeah.
software that is there, they are open source. So, for example, if you type DS9 on Google, it will show you the page to DS9 astronomy software, and you can download it to your PC. So they are not hidden. Yeah.
Yes, but it's better to add DS9 astronomy because we had
Yeah,
we have
simple. Yeah,
a
simple. Anything you're doing, DS9 astronomy, and then what I'm saying is, in case supposedly they forget the link, they can still search and
yes. For
find
example, we have
in Google.
a Star Trek Deep Space Nine series.
Yeah.
So
Okay, I think that's all. We've already gone past the time. Please take your time and go through the resources and familiarize yourself. If you can, I think you can also form yourself a group to learn and discuss about your progress. Thank you very much and have a great evening.
goodbye, everyone.
Bye.
Goodbye. Thank you.